Good morning, I'm Maheswari, APEEE department. Now this video I am going to present about the subject high voltage engineering in that third unit, that is the generation of high voltage and high currents. So in the third unit, generation of high voltage and high current, we are going to see about the introduction part of the generating high DC voltage. What is the necessity of generating the high DC voltage? So, in the electrical engineering and in applied physics, the high DC and high impulse are required for many applications. Applications such as electron microscope, X-ray, and we require high DC voltage of about 100 kilovolt or more than that. And the electron precipitators, particle accelerators, it requires a DC voltage of about several kilowatts and even megawatts. So there is a very high necessity for generating the high DC voltages. And what are the applications of this high DC voltages? This electron microscope and X-ray units are the applications, and they require an voltage of about 100 kilovolt or more than that. And HVDC, it is required for insulation test on cables and capacitors and electrostatic precipitators. And in HVAC, we require a high voltage of greater than about 400 kilovolt for testing the power apparatus for extra HV transmission line. And when high impulse voltages are required for testing purpose and in order to simulate the voltages due to lightning and switching surges. So the generation of high voltage in laboratory for testing purpose is very essential. And for high current testing, it is required to test the surge diverters or the capacitors or the switch gears, and we need to trip this current generators. So we are going for the generation of high voltages and high current in order to test the apparatus. So the circuits which is used to generate the high voltage DC are half wave and full wave rectifier circuits, voltage doubler circuits, voltage multiplier circuits, and Van de Graaff generators. So in this video, we will see about the half-wave rectifier circuit. So the diagram represents the half-wave rectifier circuit, single-phase half-wave rectifier. So the supply, and this A and B represents the representation of secondary winding of the transformer, and this is the primary winding of the transformer. And then the secondary side, a diode is connected, and the capacitor is connected in across the load resistance RL. So we know the working of this half-wave rectifier. During the positive half cycle of the supply voltage, a diode D is forward biased and the current flows from the secondary side winding towards the diode D through the load resistor and to the negative of the winding. So here in this during the positive half cycle, there is a flow of current and there is a output voltage generated across the resistor RL. And during the negative half cycle, here A terminals become negative and B terminal become positive because of the reversal of the supply voltage. And because of this negative in the A terminal, the diode D is reverse biased. So it acts as an open switch. So there is no flow of current during the negative half cycle of the supply voltage. So hence the output voltage is 0 during this interval. So this is the working operation of single phase half-wave rectifier. Now this is the diagram part for the half-wave rectifier circuit. So during the positive half cycle, I am able to obtain a voltage waveform which is similar to that of the input sinusoidal waveform. And during the negative half cycle of the supply voltage, the output voltage is 0. And during the next half cycle, again the output voltage repeats same as that of the supply voltage. So this is the output voltage waveform for a single phase half-wave rectifier. This dotted line represents the output voltage waveform of the single phase half-wave rectifier, whereas this blue line represents the output voltage waveform of half-wave rectifier with the effect of capacitor. So with respect to the capacitor charges to a value and then discharges, and then it is discharging rate is such that it is not reaching the 0 value, and when the next cycle repeats, it is again charges and discharges. And here you can see that this is known as the ripple in the voltage. So this capacitor discharge rate depends upon the capacitor discharge rate. So this is in case of a single phase half wave rectifier circuit. So the ripple factor is given by ripple magnitude by mean value, that is delta V by Vd. Now test should be done in order to identify the ripple factor whether it is more than or less than the 5%. With the capacitor C, the pulsation of the outputs are reduced. The capacitance C, you can see that the output pulsation are reduced. So assuming that the transformer has small internal resistance of the diode during conduction, the capacitor is charged to V max. Okay. Now this is your diagram for full wave rectifier circuit. So in single phase full wave rectifier circuit, here you can see two diodes are present in the secondary side transformer. It is connected. One, the first diode is represented as name A and the secondary diode is represented as name B. Now the working principle of this full wave rectifier circuit, during the positive half cycle, here terminal is positive here and the other end is negative here. This is the O terminal, negative here, and the other part is positive and negative here. Because of this polarity, the diode A is forward biased. A is forward biased and the power flows from this manner from the next secondary cycle, A forward biased through the load and to the midpoint of the configuration. This is happening during the positive half cycle. So I am able to obtain a positive sinusoidal waveform, which is similar to that of the supply voltage waveform. This is without the effect of capacitance. This dotted line waveform represents the output voltage waveform of single phase full wave rectifier without capacitance. And during the negative half cycle, this terminal is negative and this terminal is negative and here the O point is positive, and in the lower side it is negative and positive here. Because of this polarity, the B rectifier gets forward biased, B diode gets forward biased, and the power flow is like this from the negative end of the transformer to the diode D and to the load RL and to the negative midpoint, center point, O point of this secondary side of the transformer. So during this half cycle, you can observe that the flow of current is in the same direction as that of the positive half cycle of the supply voltage. So in this way, we are able to get an output voltage waveform in a rectified manner, which is the waveform is same as that of the sinusoidal voltage waveform. Okay. And here, this blue line represents the voltage waveform with respect to the capacitor. So with the help of capacitor, we are able to observe that the pulsation of the output voltage is reduced. So we are able to generate an high voltage with the help of this half wave rectifier and full wave rectifier circuit. Now for applications of high voltage of 50 kilovolt and above, the rectifier valves are mainly used. And in modern high voltage lab and testing installation, the semiconductor rectifier stacks are commonly used for producing the DC voltage. Mostly silicon diodes with a peak inverse voltage of 1 kilovolt to 2 kilovolt are used. And for lab application, the current requirement is less. So a selenium element stack with peak inverse voltage of 500 kilovolt can be used. So both half wave and full wave rectifiers produce DC voltages which is less than the maximum AC voltages. And also the ripple or the voltage fluctuations can be reduced with the help of a filter element which is connected to the circuit. So thank you everyone.